For centuries, it was a mystery hidden in the glare of a titan. Does Betelgeuse, the massive red supergiant, have a partner? Using interferometry, astronomers have just seen the unseeable, a fragile companion star tucked impossibly close to the giant's outer layers. But Betelgeuse is a dying star, nearing its final, violent supernova. What is the fate of the star in peril? And what does this cosmic drama tell us about the countdown to the explosion in Orion? What happens when a dying giant star shares space with a fragile companion? Astronomers have just seen this cosmic drama unfold for the first time. Betelgeuse, the massive red supergiant, appears to have a partner. And that partner may not survive much longer. We'll explore the data behind this discovery, how scientists separated the light of the giant from its faint neighbor, and what it means for predicting Betelgeuse's long-anticipated explosion, seeing the unseeable. How astronomers found Betelgeuse's faint companion. For centuries, astronomers have debated whether Betelgeuse, the red supergiant glowing at Orion's shoulder, might have a hidden partner. Early telescopic sketches hinted at irregular light, but instruments of the time blurred every detail into the same red haze. The question lingered. Was Betelgeuse solitary, or did a smaller star orbit unseen, concealed by the supergiant's intensity? That mystery kept resurfacing each time new technology improved our view of the sky. Yet the answer always slipped away in the glare. Betelgeuse itself invites obsession. It's a dying star whose radius could stretch past Jupiter's orbit if placed at the center of our solar system. It swells and dims unpredictably, sometimes changing brightness by more than a factor of 2. These fluctuations come from pulsations, layers of gas expanding and contracting, and from giant plumes of material cast into space. Each shift reminds scientists that Betelgeuse is unstable. Its end may come soon by astronomical standards, which makes any possible companion both intriguing and difficult to observe. Detecting another star near Betelgeuse is like spotting a candle beside a spotlight. A faint companion's light would merge with the supergiant's and vanish into the same blurred image. The problem is one of contrast and angular resolution. How distinctly telescopes can separate 2 points of light that are close together. Until recently, even the largest ground-based mirrors blurred the 2 sources into one because of shifting air currents and the star's immense brightness range. This is where interferometry changed the game. Interferometry links multiple telescope mirrors, so they act as one huge mirror spread over hundreds of meters. The technique combines light waves to increase resolution, allowing astronomers to resolve structures otherwise hidden. Adaptive optics added the ability to adjust in real time for Earth's atmospheric distortion. Each small correction sharpens the focus slightly, and when the signals from several telescopes are combined, fine details begin to emerge from what once looked featureless. Past attempts to find a companion to Betelgeuse ran into familiar roadblocks. Dust clouds surrounding the star often block visible light and scatter infrared emission. Betelgeuse's irregular dimming further complicated measurements. At times, the star's brightness can drop suddenly, making it hard to model its true surface shape. Even space observatories struggled because optical detectors saturated easily, producing glare halos that hid any secondary source. The resolution limit remained a barrier. The turning point came from data gathered using the European Southern Observatory's Very Large Telescope Interferometer, sometimes cross-checked with measurements from ALMA, the Atacama Large Millimeter/Submillimeter Array. Observers noted subtle but consistent differences in wavelength between 2 overlapping signals. When they mapped those differences across time, a pattern of separation appeared, repeating as if 2 sources orbited one another. This spectral distinction, slight variations in color and temperature suggested that not all the light came from the supergiant itself. Models that match the observations point toward a smaller, hotter star tucked remarkably close to Betelgeuse's outer envelope. A long-standing hypothesis predicted such a companion might exist, helping explain some of Betelgeuse's irregular mass loss. With the interferometric images now supporting that prediction, the argument that Betelgeuse is a single star has weakened considerably. Uncertainty remains about exactly what that signal represents. Some researchers caution that the apparent second source could be a dense, bright knot within Betelgeuse's own stellar wind, rather than a self-contained star. The data will need confirmation through repeated observations at different wavelengths. Still, the consistent spectral offset strengthens the case for an actual orbiting companion rather than mere atmospheric structure. For the first time, astronomers can point to direct evidence instead of inference. A separate light source stands out from Betelgeuse's overpowering glow. This discovery answers a question older than modern astrophysics and reframes how scientists model red supergiant evolution. Yet it also raises a new and troubling question. If Betelgeuse is truly nearing its final outburst, what becomes of a companion that never had room to escape? A star in peril. The fate of Betelgeuse's companion. The discovery of Betelgeuse's faint companion raises an uncomfortable question. Can a smaller star survive beside a red supergiant nearing its explosive death? Binary systems with one massive and one lighter star are common, but the balance becomes fragile as the heavier one runs out of fuel. Betelgeuse has already used hydrogen and helium in its core. It now fuses heavier elements such as carbon, neon, and oxygen. Each new stage burns faster than the last because nuclear reactions at such high temperatures release energy less efficiently. Once the core consists mostly of iron, fusion stops producing power. Gravity takes over, the core collapses, and the result is a supernova. That event releases more energy in seconds than the sun will emit in its entire lifetime. For a nearby companion, this isn't a passive show. In close binary systems, the stars exchange material through a process known as mass transfer. When one star swells enough that its outer layers come under the gravitational influence of the other, gas can flow across the shared region between them, an area astronomers call the Roche lobe. The receiving star gains mass and spins faster, while the donor star loses both matter and angular momentum. Over time, this interaction can distort the star's shapes and pull them into elongated orbits. In extreme cases, the smaller star may even spiral inward and plunge into the larger star's envelope, forming what's known as a common envelope system. Evidence suggests Betelgeuse is already losing matter at a rapid rate. Its stellar wind, streams of charged particles blowing outward, moves thousands of times faster than any solar wind we know. That wind carries dust and gas into space, forming a complex shell around the star. A companion orbiting near such turbulence faces constant bombardment. As Betelgeuse sheds mass, its gravitational pull weakens. The companion's orbit can then shift outward or become unstable, depending on how fast the mass loss occurs. If the wind thickens into clumps, the smaller star might be partially engulfed, disrupting its surface temperature and atmosphere. Observations of intermittent dimming episodes in Betelgeuse hint that the surrounding dust cloud grows denser at times, a sign that this process is active now. Astrophysical models over the past decade have explored what happens when a red supergiant swells enough to touch a nearby partner. The consensus view is that if the distance between them is less than a few astronomical units, the lighter star could become trapped inside Betelgeuse's extended atmosphere well before the explosion. Inside that envelope, drag forces slow its orbit, leading to further in spiral. Some hypotheses predict this merger might ignite jets of gas that carve cavities through the envelope. Those cavities could later channel the energy of the supernova into specific directions, creating an asymmetric blast observable from Earth. Other simulations show a contrasting scenario. Instead of being swallowed, the companion might remain at just the right distance to sculpt Betelgeuse's wind into a spiral pattern. This shaping could influence how the supernova ejects matter into space and how its brightness evolves over time. Astronomers studying remnants of other supernovae often find uneven debris patterns that suggest a hidden companion once played a role. Interferometric measurements hint at a faint bridge of material between Betelgeuse and its partner. That bridge could be an arc of gas drawn from the supergiant's outer shell, or a stream formed from direct mass transfer. If confirmed, it would mean that the two bodies are still exchanging matter, even during the star's late phase. Such evidence helps scientists estimate the companion's risk. If the connection persists when the core collapses, the shockwave and radiation burst would likely vaporize any exposed surface. Some researchers argue the companion might survive, but lose most of its outer layers, becoming a stripped stellar remnant, moving at extraordinary speed. For now, the system offers a natural experiment in how massive stars approach death. Observing the ongoing interaction between Betelgeuse and its companion, however fragile it is, may reveal how stellar explosions unfold and how binary dynamics dictate what comes next. Understanding that link broadens our grasp of how other fading giants communicate their countdowns through subtle changes before they collapse. Conclusion: Betelgeuse now serves as a kind of cosmic clock, marking each shift in brightness as a signal of its changing interior. Every new observation offers hints about how massive stars exhaust their fuel and reshape their surroundings. The sight of a vulnerable companion beside such a giant highlights that stellar partnerships often end through destruction. Yet those same violent endings enrich space with the materials for future stars. As new telescopes refine their view, every small change in Orion's shoulder could reveal another step toward Betelgeuse's final act and deepen our understanding of how stars live and die.